That was the whole reason I got school.
All right, let's get down to business. All right, you have a mini exam due on Monday. The third one is due on Monday. And then I have your new one today.
When's that one due?
Well, you're about to find out. I don't even know. It's on top of this. 3, 4, 2, 3, 4, 1, 2. So I recommend that you do this one because in terms of level of difficulty, this one is on the lighter, easier side of things. 6 questions, and this is the first mini exam where you really don't have to go digging around into like Cal 1, Cal 2, weird things, making, connections between things. This is a very straightforward, direct computational type exam. So it's a little tedious. I will admit it's a little tedious, but it is, there's no tricks here, all right? So that is due the 8th, right? Okay. All right. We were talking about chain rule last time, right? And we almost finished up that section. We're going to wrap that up. And we're going to get into a section I'm really excited about because we're going to learn something. We're going to learn that to do something really hard is actually turn out to be really easy, and it's a little surprising. All right, we'll see. All right, so back to the lecture notes from last time. We are going to talk about implicit differentiation. We were doing last time just chain rule stuff, and now we're going to talk about implicit differentiation when we have equations that contain 3 variables and we cannot isolate the z. So at the beginning of class last time I talked to you about how in Cal 1 when we had equations with x and y and we can't isolate y, that's when we brought in implicit differentiation. Well, we're going to do the same thing now but when we have equations with 3 variables. So let's start off here with this. I'm sorry that's so small, I'll make it a little bigger. So suppose that we have z is equal to a function of x and y, all right? So somehow you can determine z if you know what x and y are. What we're going to do is we're going to rewrite the equation where we bring the right side of the equation, we're going to subtract it on both sides and get this equation, right? That's algebra. And then what we're going to do is we're going to define a new function. And this function that we're going to define is capital F. And what it's going to be the left side of this equation. So forget the equals 0. That right there, that equation is an equation that contains x, y, and z, right? So it's an equation containing 3 variables, x, y, and z. And capital F depends on the value of the x, the y, and the z. So, what we do now is we're going to take this equation, we're going to set this thing equal to 0, which would match with this equation up here. We're going to differentiate it implicitly. So let me draw you a picture, a tree diagram like we did last time. We have this capital F, and it depends on 3 things, x, y, and z. But we also have that z, remember in the very beginning we said that z depended on x and y, right? Do I need to show it again? No? Z depends on x and y. So we know that z depends on x and y. And if you remember from last class, there was a problem we did at the very end where one of our branches on our tree didn't have the variables that appeared in the other branches. So what I did is I just put them there and I said, okay, when we differentiate those, they're probably going to go to 0 or something like that, but we're going to include them in our diagram. So this is going to look strange. I'm going to do it in a different color. But would you agree that I could say that x depends on itself?
Yeah.
Yeah? And I could say possibly x depends on the y. You give me y, I may be able to determine what x is. And I can say the same thing for the y. The y may depend on x, and the y may depend, or well, y always depends on itself, right? Y is whatever value it is. So I can do that even though these weren't explicitly given to us. We can deduce that just, yeah? This gives me a full tree. So what are the possible derivatives I can ask for now? I could do the partial with respect to x, right? I could do the partial with respect to y, right? The partial of capital F, right? Yeah. Partial of capital F. So let me do this. Let's figure out what would be the partial of capital F with respect to x, right? Partial of capital F with respect to x. Guess what I'm saying on that is where is this in our tree? Do y'all see that partial in our tree?
Yeah.
Right here? What's from here to here? Partial F with respect to x, right? Hold on, let me write our original. We were taking this function of x, y, and z, and we were setting it equal to 0, right? Let me just write all the branches first before I do any more. This would be partial x with respect to x. What do y'all think that should be? 1. Down this side, partial x with respect to y, right? Let me do here. Partial y with respect to x. Partial y with respect to y. That'll be 1 as well, right? Partial z with respect to x. Partial z with respect to y. And then this one right here, partial f with respect to x. Let me do something real quick. Where is it? Oh, z, yeah, thank you. Z, I forgot the middle one. Partial f with respect to y. All right.
Question.
Hold on. So before I go too far, remember we started with this, right? Z is some function of x and y, right? So if I had this picture, right? If I have that picture, then what partials are possible from this picture? Partial of z with respect to x, partial z with respect to y. So this is where we're starting. The entire thing is we have this equation that relates x, y, and z. I would like to know what these two derivatives are. All right? So what I did was I moved everything to one side, called it capital F, and then I created the tree from that capital F. And what I want you to see right from this is that if I wanted to know what this is, do you all see that appears in this tree somewhere? Where is it? Right there, right? It's in this tree, right? So maybe there's a way I can solve for this somehow. And so, again, the previous page said move everything to one side, so z minus f of x, y. This is capital F of x, y, z. And then we set that equal to 0. I'm setting it equal to 0. I set it equal to 0 because if I move this to the other side, then I'm going to have a 0 on the right-hand side, right? So if I'm calling that left side capital F of x, then solving this equation is the same as solving that equation. All right, so if I differentiate this, imagine I differentiate this, I'm going to use this table for that differentiation. So let me see if we're trying to solve for this right here. If we want to do this, then what I need to do is see what the derivative of this capital F looks like where I can pick up this branch. So wouldn't that be with respect to x? Yes? So if I go with respect to x, I have to go down here, right, that branch plus what? That branch. right? Plus this branch right here, right? I'm going to write that down, then I'll answer your question, all right? So I know that the partial f with respect to x times partial x with respect to x plus partial of f with respect to y times partial y with respect to x plus partial f with respect to z times partial z with respect to x must equal 0, because I'm differentiating both sides of this equation with respect to x. And this is what I get. Y'all see it's just the branches, this branch plus that branch, down the x variable sides. I have a look. Okay. At the end of this all, we're just going to get a formula, okay, that we're going to use, but I'm trying to show you where the formula is coming from. So I want to know what this is. I want to know what that is, and I see it right here in the equation, all right? If I want to know what the partial of z is with respect to x, what variable am I holding constant? If I want to do the partial of z with respect to x, the y variable has to be held constant, right? So come back over here and let's reevaluate this thing. If we're looking for the partial of z with respect to x, okay, what that tells us is that this will turn into, let's see, partial of f with respect to x times, we said partial of x with respect to itself is 1, plus partial of f with respect to y times, now, what's that? We're holding y to be constant. So what's the derivative of, if y is a constant, what's the derivative of a constant with respect to any variable? 0, right? So this is 0, plus the partial f with respect to z times the partial z with respect to x. Again, equals 0. Again, the thing I'm trying to solve for is right here. So that's not x. I said x, I wrote z. All right, this is gone. And so what I'm going to do now is I'm going to move this to the other side of the equation. Okay, so what I get here now is this. These two factors, partial f with respect to z times partial z with respect to x equals negative partial f with respect to x. So that's just moving that to the other side. And then finally, to get this by itself, we just divide through by that partial. So we get partial z with respect to x equals negative partial f with respect to x over the partial of f with respect to z. So I know a lot of this is confusing. Let me wrap it up in like a statement. If we're given an equation that contains x, y, and z, and we cannot solve for z explicitly, we can't get z isolated on one side of the equation, then what we can do is move everything to one side of the equation, call that capital F, and then to find the partial of z with respect to x, all we have to do is the negative partial of f with respect to x, capital F, divided by the partial of f with respect to z. We do that, and we will have the partial with respect to x. Similarly, we could have asked for the other branch, like the other side. I could have asked for the partial of z with respect to y. And what we would do is the exact same thing, but we would differentiate with respect to y. Do you all want me to do it, or do you want just the formula that comes out at the end? Yeah.
You're differentiating the equals 0 one.
The equals, I'm differentiating the equal.
Like the f, and I was up one more row. Is that what you're doing?
Yes, we're differentiating this
Okay.
with respect to x. Yes, exactly. Okay. All right, that formula, I'm going to come back to that formula. Let me put it over here so I don't have to bring it up on the screen. So negative partial f with respect to x over negative partial f with respect to z. Okay, that is our first formula for implicit differentiation. And Why did I put negative twice? I don't know why I did that. All right, so y'all didn't answer. Do you want me to derive the other formula and do the tree and do it all again? Or do you just trust that I would be able to solve? Was there a question back there?
Doesn't the partial f cancel out in that equation?
No, because we're not treating this like a true fraction, right? This is not like a true fraction where these numerators, this is an operation, right? We're taking a derivative of a function with respect to a variable. So this notation, we don't want to treat it like a true fraction. Understand?
Yeah.
That's the problem with Leibniz notation, is that sometimes we cancel even though technically we're not canceling, and it makes people, or reducing, and then people get the idea that you can always do that, and it's a little dangerous. So in this case, no, but does it kind of make sense that if you did flip this up, it seems like it's at least trying to get close to this, but it'd be off by a sign. So, but that's technically, we're not allowed to do that. Okay, so I'm just going to give you the formula for the other one. If we want the partial of z with respect to y, it's this same thing, except there's a y right here instead of an x. So it's negative partial f. I want to make sure I put these formulas on the sheets for you. There, that's it right there. So these are in your formula sheets, all right? And I actually, in the formula sheets, I show you what the partial like the tree looks like when you take the branches of the tree. If you want to, you can go back and kind of check for yourself. If you do, just keep in mind that now in the tree, this becomes a 1, and this becomes a 0 because you're holding x to be constant. So this one goes away, this one stays. Where in the other one I did, it was the opposite. So you're probably most concerned, at least at this point, with how to use this. It's just a shortcut, and so we don't have to grind out a bunch of arithmetic. So here's the problem we're going to do. So remember, try and put yourself back in Cal 1, way back then, right? And we had an equation with x and y in it, and we couldn't solve for y, but we wanted to know the derivative. Well, we used implicit. Here we have x, we have y, we have z. They're all mixed up. It's in an equation. I would love it if I could get z by itself and get x's on the other side. Then I would just do what we did last class. But here, it would be extremely difficult to get z by itself. Y'all agree with that? I mean, you got z cubed here, z, so maybe you take that stuff over, but then you factor z out, you still have a z squared. You're not going to have an easy time getting z alone, right? So I'm not even going to worry about that. What I'm going to do is I'm going to bring everything to one side. Okay, so I'm going to take x cubed plus y cubed plus z cubed plus 6xy z minus 1 equals 0. Okay, so I moved everything to the left. And then I'm going to call this my capital F. All right? And then what I'm going to do is I'm going to take some partial derivatives. Right? I'm going to do these right here. So let's find first partial of z with respect to x. So according to the formula, I need these two things, right? I need to get these two things. And then, divide. So negative partial f with respect to x divided by partial f with respect to z. Now look, there's a subtle important thing here. When we are doing partial derivatives, right, when we started this whole discussion, when we did a partial, we had to hold something constant, right? So if we did the partial with respect to x, we held y to be constant, right? If we did the partial with respect to y, we held x to be constant. Well, here, our capital F is a function of 3 variables, right? So if I want to do a partial of f with respect to x, what do I have to hold constant? The other 2 variables. Both the y and the z are going to be treated as constants, both of them, all right, when I differentiate. So let's try that. I want you to look at this right here, okay? Just ignore the 0 because we're looking at this as a function. And let's talk about what the partial of this is with respect to x, treating y and z like constants. So derivative of x cubed would just be your traditional 3x squared. And then the derivative of y cubed would be 0 because y is a constant, so a constant cubed is still a constant. And then the derivative of z cubed would also be 0 because we're treating z like a constant. All right? Gone. All right, this does not go away though, right? 6 is a constant, y is a constant, z is a constant, x is not. So what would I get there? 6yz. Plus 6yz. That's the derivative, yeah. I'm going to put, you can put the negative out front or wherever you want, really. I'll put it up here if you want. Didn't really give myself enough room for it, did I? And then we're going to do the same thing, but now we're going to take the partial of this, let's see, with respect to z, right? If I do it with respect to z, that means I have to treat both x and y as constants. So partial of that with respect to z, the derivative of that would be what? 0, 0, 3z squared. And then the next term will be very similar to what we got above. Z is the variable though, so we'll just get 6xy. That's it. That's it. So check this out. Let's see if we can't wrap our heads around what's going on here. I'm thinking, how far do I want to go back? Let me go back a little bit. Because I think you have to make a real good big connection here. Let's go back to Cal 1. Let's take this equation right here. It's a circle, radius 3. If I want to talk about a tangent line, the slope of a tangent line, right, dy dx, if I want to figure out what that is, I need to go to some point here and find that slope. I'm going to need to take the derivative of this, right? So if I do that implicitly, if I take this equation, I take the derivative with respect to x on the left and the derivative with respect to x on the right. The derivative on the left is 2x plus 2y times y prime or dy dx. I'll put dy dx equals what? 0. And then I can solve for dy dx by moving things around, right? So if I move things around, I get dy dx equals negative x over y. If you just move this over and then divide by 2y, you get this. Okay, I'm showing you this because this is implicit differentiation in Cal 1. What this formula says is that in order for me to tell you the slope of the tangent line, what do I have to provide you? The x and the y. I actually have to tell you exactly where I am, right? Before implicit differentiation in Cal 1, when you can solve for y, you only have to give the x value for the derivative, right? The x value. But when it's implicit, like this, you have to give me the exact point because for that x value, there is another point down here that has a different slope, right? So you have to be able to distinguish between these two, and that's why the formula has the x and the y in it. Got it? We're doing the exact same thing right now. We started out, and we have, look at this example. This is an equation with 3 variables, right? So we have a surface. Now this surface doesn't have to be a true function, like it could be, I don't know, like an ellipsoid, something like that, right? This is a surface. And if I want to go to a point here and talk about a tangent, right, a tangent line, well, I can only do partials because I have to like point in one direction or the other direction, right, and hold something constant. Well, what if I do that, let's say on the ground here, you know, this is the point I'm plugging in to get to that. that point right there, I'm going to be able to talk about partials there, my slopes in different directions. But there's another point down here, isn't there, on that surface? And so there's going to be different derivatives down there potentially, which means that our derivative should require what? X, Y, and Z. And you can see it does. Do you see that our derivative, the derivative with respect to X of this surface is going to be something where you have to give me the X, the Y, and the Z, and then I can tell you what it is. Yes?
Wouldn't there be a mirror point along each axis?
Well, it depends on the surface, right?
Specifically something
Like on this,
like
yes.
here?
Yes, on this, yes. You would have a point on the bottom as well. But this, an equation with 3 variables doesn't have to be like a closed surface. It could be like the saddle that we saw. Yeah. So sometimes yes, sometimes no.
Quick question.
Mm-hmm.
Is that homogeneous?
What's your definition for homogeneous?
I'm just trying to remember. I don't remember if the 1 kills it.
What do you mean homogeneous can be?
Like from differential equation.
Is it a homogeneous equation?
Yeah.
Differential equation?
Doesn't have any difference.
There's no differentiation in there. Yeah.
All right.
Yeah. Well, there's no derivatives in there, right? So it's not a differential equation.
Finish. Sorry.
No, it's all right. But I see what you're starting to see, like patterns and things, I guess.
Yeah. I thought they were all third power from the same one.
All right, should we do this one?
Sure.
Yeah, may as well. Partial z with respect to y. Does anything change? What changes? Well, the bottom's the same, right? It's the same thing for both of them. So that's going to stay the same. And that was 3z squared plus 6xy. And then on top I have negative, and then the partial of f, this time with respect to y. So not a lot changes there either, right? It's going to look really similar to the one that we had before. It's going to be 3y squared plus 6xz. There you go. So now, because where we're about to go in this section, in the next section, let's just kind of imagine that somebody gave me a point on this surface, right? So somebody gave me an x, somebody gave me a y, and somebody gave me a z. So I'm not going to get my 3-dimensional space out, okay? But I go out x, right? I go out y, I go up z. Now I'm like sitting here, there's the point on that surface, right? Okay, if we hold the x to be constant, right? Partial with respect to y, we're holding x to be constant, then let's see. Maybe I do need 3. I'm going to get it because I'm going to need it for the next section anyway. See if I can do this without cutting my fingers off. It's like a Rubik's Cube. There we go. All right. All right. Everyone, can you all see this enough in the back? Okay, remember red is what axis? X, Y, Z, right? So I pick a point on the surface. I go out X, I go out Y, I go up Z. Here I am, right? If I'm doing this partial, then I'm holding X to be constant, right? So I'm holding this to be constant, so I'm fixing it, and there's a plane slicing through my surface here. And what I see on that is a curve. And to find the slope of the tangent line on that curve, I use that formula right there, which means I just give you the x, the y, and the z that that takes you to that point. I plug it in here, and that will give you the slope of that tangent line. Understand? Where's my line? That'll give you that right there. Okay? The one we did right before this is the same thing, except we go out x, y, z. Now we hold our y to be constant, so we slice through this way. And we have a curve that goes like this, and we're finding the slope of tangent line right there. Right? Yeah. Did you all see that visually? Like, I see it, but do you all see it? Yes? Kind of? Do you see the plane? Do you want me to show y'all the image again? The one that I'll show it because I mean this is important for the next section. If we're not seeing it, it might be hard to see what we're about to do. Hold on. Trying to remember where it was. 10. No. 4. No. 11.3. There we go. Is this picture right here. We have a surface. We have a point on that surface. Can you all see the point right there? Okay. And what we're going to do is we're going to hold our y value. Let's fix the y value first. If I fix the y value, hold it constant, then I'm taking the partial with respect to x. If I do that, I'm slicing through with the plane. You see, this is my x-axis, right? My y-axis goes this way. So I'm holding my y to be constant. So if you come in from the side, do you all see I'm holding my y value to be constant right here, which slices through and creates a function. If you look at it from the side, it looks like that, where it cuts through. And what we're doing is we're trying to find the slope of the tangent line at that point on that curve. So it reduces to a Cal 1 problem. That's if we hold y constant. If we hold x constant, the difference is the way the plane slices through at that point. So we hold x constant, now our plane slices that way. See, my x value is being held constant here, and so we get a different curve. You'll see that kind of purplish curve versus the curve that's green. Let me take those out. And so we get a slope that way. So we have two perspectives, one where we hold y constant, one where we hold x constant. We get two different, well, they don't always have to be different, but most of the time they're different slopes. Yes?
What is happening when you take the partial for x and then the partial for y?
What do you mean?
That was something that we covered, I think, last week, was when you have the f and then you have the subscript x, y.
Subscript.
You take the partial of x and then you take the partial of y.
Oh, it's just a second derivative, that's all. So you're saying what is it visually?
Yeah.
There's not as easy a connection to that. There is, not all of those make geometric sense. Some of them do, and we're actually going to talk about it, not this section, but the one after. So where do those second partials come into play, right? They will. They're going to help us, actually, they're going to help us determine the highest points and lowest points on our surface. We're going to have something called the second derivative test, just like we did in Cal 1, except it's going to involve second derivatives, but partial second derivatives. So stay tuned.